My name is Diego Serrano. I'm a MEMS development engineer at Qualtrics. I'm also a member of the integrated MEMS group at Georgia Tech. And in this session, I'm going to be covering the design and analysis of MEMS accelerometer. So I just covered the gyroscope session. So if anyone notices that I'm running out of steam, just start asking a lot of questions so I stay awake because it's been a long day. So I think an appropriate way to get this this discussion started on MEMS accelerometer is probably by looking at the future of this type of devices and ask ourselves if MEMS accelerometers are still relevant. And if we take, for example, a particular market, in this case, the mobile phone or tablet market, we see that for the past 5 years or so, there has been a significant increase in the market share of different MEMS sensors, including accelerometers, gyroscopes, and integrated magnetometers. But when we look at the projections for the next 4 years or 5 years, we see that even though there's still some room for growth in integrated magnetometers and gyroscopes, it seems that standalone accelerometers are going to be declining in terms of market share. So then you might ask yourself, well, then what's the point on attending on a discussion about MEMS accelerometers is if things don't look so bright. And if we take a closer look, what is actually happening, particularly in this application space, is that we have this new breed of inertial sensors that are usually referred to as multi-degree of freedom combos. And what this actually are combinations of accelerometers, gyroscopes, and magnetometers, but in the same package. And if we see the projections for this type of sensors, actually it seems that things are going to keep growing for the next few years. Now, something important to highlight here is that what this is generating is a shift in paradigm in the way we design our sensors. So when MEMS technology first started, especially in the inertial space, people were worried about designing their accelerometers, designing their gyroscopes, but this new trend tells us that actually we should be looking into designing for integration. So how can we make these different types of sensors coexist, and how can we put them together, for example, in the same vacuum environment? And this shows an example of how to do this. I talked a little bit about this device in the previous session, but basically what this shows is that you can actually incorporate both rotation and acceleration sensors in the same package, and then get a lot more advantages in terms of size when you're going to try to put this in, for example, a handheld device. Now, what I just discussed is a particular application space, which is the consumer market. But if we take a look at other sectors, like for example the automotive industry, there's still a lot of room for the development of standalone accelerometers. So they're still being used for airbag deployment applications, and in combination with gyroscopes for rollover and anti-skid control. And since there's no much of a size constraint, you can still keep these devices separate. Similarly, in the industrial space, as we discussed in the gyroscope session, there's still a lot of room for improvement in terms of survivability and shock immunity and vibration immunity. So what I really want to point out here is that something that is critical when we're designing this type of sensors is to keep in mind the requirements for a particular space or a particular application, and that's something that we're going to be discussing throughout today's talk. Similarly, when we look at the consumer space, well, in this particular example, what we want is to design smaller and low power consuming devices, and as we discussed before, there's this new set of applications targeted to inertial navigation, which are actually requiring for sensors that are not only smaller and low power consumption, but also need to have very good resolution or high, low noise specifications. In a very similar way, the military space is demanding for this type of devices in which you can incorporate accelerometers and gyroscopes into a handheld monitor that can, for example, keep track of how a soldier is moving without having to rely on a GPS signal. So the reason this is still a very exciting field is because there's still a lot of room for improvement in this type of sensors. So again, a good way to understand how where the performance metrics of MEMS accelerometers are today is good to look back and see how the devices have evolved over time. So if we take a look at the probably most typical example, ADI's accelerometer for the automotive industry, which, as probably most of you know, was a very successful story because it was the first commercial MEMS accelerometer. One thing that we see here is that there's definitely an evolution towards smaller size. Now, in this particular example, we see that most of the size improvements were done in reductions on the circuit and not in the MEMS itself. But if we see what's happening in consumer electronics nowadays, we see that there's still this trend to make things smaller, and it's actually happening in the sensor. And this, in combination with different packaging schemes, like for example die stacking, where you take your MEMS sensor and then you put your right on top of it, we can achieve very small form factor devices that can actually fit into this particular case on SDI microelectronics 2 by 2 by 0.9 cubic millimeter package. Similarly, if we take a look at Bosch Sensor Tech's standalone accelerometer, they went through a very similar path. They started with a 9 millimeter squared area package, and they also went from a side-by-side approach to a die stack approach, and then with reductions using both the electronics and the sensor. Now they have, as far as I know, the smallest commercial accelerometer in the market, and this device is actually quite small, including the molded package itself. It's only 1.5 or 1.2 by 0.8 millimeters, cube millimeters. But even though this reduction in size is very interesting, as we've been mentioning, what really is critical for the future is the incorporation of these different types of sensors in the same package. And here we can see some examples of a few companies that are already starting to do this. And we see, for example, ST Microelectronics, they have their gyroscope co-integrated with the accelerometers, and I think in the first session there was a question regarding the spacing between the two of them. I think you have that. And I'm not entirely sure, but if I were to take a guess, the reason you need that spacing is because accelerometers and gyroscopes usually operate in different environments. As we saw for the gyroscopes, if you want high Q, you need very low vacuum pressures. So when you have a tuning fork device, and for accelerometers, you want to avoid the low vacuum because you don't want Q peaking. And this is something we will discuss in detail in a few minutes. So obviously, this new trend of integrated sensors is what is really driving the change in the way we should take a look at how we design our devices. And going back to this personal navigation applications, the question is, well, how can we take this big inertial measurement units that we usually find in satellites and rockets and airplanes and make them around the size of package that can fit into a phone. And obviously, in order to be able to do this, we need, particularly for the consumer market, we need to take a look at different items. So first, as we mentioned, we need to be able to co-integrate this with gyroscopes. So fabricate both devices using the same fabrication platform, because that gives us a size and a cost advantage. If we want to use the sensors not only for navigation, but maybe other applications like gaming, you need to design for different parameter specifications. In the particular case of gaming, you need like a large dynamic range, because you need to measure this wide swing type of motions. And if we want, for example, to do camera stabilization, you need a very decent bandwidth. So, as I mentioned before, depending on the application, we need to look at different specifications and try to target for improvement of those particular specs. And obviously, as we saw during the gyroscope tutorial, we need very robust and very reliable structures that are immune to shock and vibration, because as we saw, vibration also plays an important role in the performance for navigation. So now let's talk a little bit about the fundamentals of operation of MEMS accelerometers, and probably an easy way to understand this is by taking a simple example. Probably the most typical type of MEMS accelerometer is a capacitive type accelerometer, which consists of a proof mass that in a 1x11 model we can describe by this M, where most of the mass is actually determined by this rectangular block in the center, which we usually refer to as the proof mass. Stiffness or spring constant that is defined mostly by the tethers that attach that free moving proof mass to an anchor location attached to the rest of the substrate, and a dashpot with a damping constant that is going to be given by mostly how the structure interacts with the environment, the air environment around it. So if we take a look at the static response of this device, we see that if we apply an acceleration, we're going to get a force given by Newton's second law of motion, which is basically the mass of the structure times that input acceleration. And as I said, in a static case, well, that force is going to be counteracted by the spring force given by Hooke's law, which is K times X. So our scale factor for the static case is just going to be the mass of the structure divided by the stiffness. So basically, the amount of displacement that we get per unit of acceleration depends on how big of a mass we have and how small of a spring constant we have. And obviously, once we have this displacement, we need to convert this into an electrical signal. In this particular example, what we do is we place electrodes, parallel plate electrodes attached to the proof mass and adjacent to fixed locations, and then we measure that changing gap that is going to be proportional to the displacement, which is proportional to our input acceleration, that is the signal of interest. Obviously, there are many other ways in which we can detect this change in displacement to convert it to an electrical signal. Another method is by using piezoelectric detection. In order to do this, what we can do is we can put a film of piezoelectric material on top of our structural beam or tether, and then when we have a difference in stress due to an acceleration that's particular displacement in the mass, that generates a change in charge that can be measured as a change in voltage. We can also use piezoresistive type of sensing, in which if we take, for example, silicon and we dope it in a particular way, we can create these regions whose resistance changes when you have a change in stress. So if you run a constant current throughout the resistor, well, this change in resistance is going to be equivalent to a change in voltage. And we can also utilize electrostatic sensing, as we described before, which is just measuring the changing capacitance due to a change due to a deflection. Now, the reason why electrostatic transaction is more attractive is because it's easy to implement. You don't require any additional materials, or you don't require the DC current for the piezoresistive sensing that actually determines how low your noise is going to be. So another advantage is that you don't have any temperature changes due to the differences in the temperature performance of each of the materials. So that's why conventionally we prefer using electrostatic sensing. And as we described in the gyroscope session, we can have either this parallel plate type of sensing in which your changing capacitance due to a changing gap is inversely proportional to your gap squared. So it has very high electromechanical coupling, but it's a nonlinear function. So there's only so much changing gap you can have before your nonlinearity starts turning performance. Or you can use this comb structures in which the change is not actually perpendicular to the gap, but you get this more linear type of function, but not as strong of electromechanical coupling. So obviously, as we showed in a couple of slides ago, generating structures for in-plane acceleration detection can be pretty straightforward. All we need to do to define the gaps that we use to measure the change in displacement is we can just define a trench in between the moving structure and the fixed electrodes. But when we're trying to do autoplane detection, things get a little bit more complicated. One easy way to do it is if we have our autoplane translational type of structure, we can place top and bottom electrodes and measure the differential changing capacitance between the moving structure and those fixed locations. The problem with this is that you usually need to process both sides of a wafer in order to define the electrode areas. So in a lot of process flows, this might not be possible, or it might be too expensive. So an alternative technique that you can use is by, for example, placing your autoplane fixed electrodes overlapping your moving mass, but also attaching electrodes to the proof mass itself, and then you can place the two fixed electrodes, for example, along the x-axis direction, and then the two electrodes are attached to the mass on the y-axis location, and you can get a differential changing capacitance when the structure moves vertically. And this shows an FEM image of this type of electrode configuration, in which you don't require a top and bottom processing to define these electrode areas. Now, in some situations, you might not even be able to have this additional layer to define your top electrodes. So for those situations, what you can do is actually use this teeter-totter type of structures, in which what you do is basically you off-center the center of mass of the structure from the geometrical center of the light. So when this experiences the z-axis acceleration, you're going to get this forward type of motion, and then if you place electrodes just on the bottom surface, then you can get this differential changing capacitance. And this shows an FEM view of ST microelectronics accelerometer, which actually utilizes this technique. And if you see most commercial accelerometers in the consumer space use this type of structures, because you avoid that additional layer on the top. Well, now that we have defined different ways in which we can implement devices to measure in-plane and out-of-plane acceleration we can start taking a look at some of the metrics or the parameters that we should look after when defining an accelerometer to make it high performance. So here I've written down an expression for capacitive accelerometer in terms of different factors. So the first term right here corresponds to the scale factor. So basically this determines how much change in capacitance am I going to get for an input acceleration. And as we saw in a few slides ago, this is basically equivalent to that static deformation that is proportional to the mass over the stiffness times whatever the change in capacitance or change in displacement is going to be. The second term is our nonlinearity. So if, for example, we are using these parallel plate electrodes, we know that this is a nonlinear transducer, so that's obviously going to generate some higher order patterns. In this case, I'm only showing the second order nonlinearity term, but you can have third and fourth and higher order components as well. This next two terms are cross-axis, so basically what this is the amount of changing capacitance that you're going to get when you apply an acceleration to the structure that is along an axis that is not the axis of interest. So basically, if we have, for example, that teeter-totter structure that I was showing, and what you want is to get this torsional motion only when you apply the z-axis acceleration. But if you have some processing imperfection and the method is slightly tilted, when you apply x-axis acceleration, you still might get a little bit of torsion, and that's going to cause a change in capacitance that is not what we were expecting. And the last term is basically the offset, which corresponds to a static signal that is there even in the absence of any input acceleration. So obviously this is another source of error. Now, in terms of the different parameters that we should look into when designing accelerometers, probably one of the most important ones is the resonance frequency. The reason for this is because this shows up in almost every other specification that we need to look for when designing this type of structure. So, for example, in the scale factor, as we saw before, that is proportional to the mass over the stiffness, which is the same as 1 over the resonance frequency squared. So, what this is telling us is that if we want high scale factor, similar to what we saw for this multi-slit gyroscope, what we want is to have a very low resonance frequency. Now, the problem with this is that if we have a parallel plate actuation, we see that our quadratic nonlinearity obviously is going to also get worse as we decrease the value of that resonance frequency. So there's always a trade-off between these two, your scale factor and your nonlinearity. So there are some electronic compensation techniques that we can use to actually linearize our response, and we'll talk about them a little bit later. The next parameter is Brownian noise. So one interesting thing here is that it's inversely proportional to this resonance frequency. So obviously, if you try to reduce that to gain scale factor, you're obviously going to be degrading your noise. But something that we should know is that there's also a mass term here. So if we try to decrease our resonance frequency by actually increasing our mass rather than by decreasing the stiffness, we can actually get much better noise performance because this is proportional to the square root of 1 over the mass, right? So obviously, increases in mass are going to have much more impact in the mechanical noise, and that way you don't have to sacrifice this term at the expense of getting a larger scale factor. Very similarly, when you look at the pulling voltage, which is the minimum voltage that you can apply between your moving structure and a fixed electrode before you get this snap-in or unstable condition, we see that, again, it's proportional to your resonance frequency. So decreasing this number affects your pulling voltage, and makes it lower. But if we play around with the mass rather than with the stiffness, your cooling actually doesn't get affected at all because the mass term cancels out here. And again, the bandwidth that is just for an overdamped system is just proportional to frequency. So obviously, higher scale factor is going to have it's going to cause a compromise in your bandwidth. But then again, there are electronic techniques that you can use to increase bandwidth very similarly. It's very similar to what you can do for your nonlinearity, and we'll discuss that. So now that we know which are the parameters that are important for performance in an accelerometer, the question is, well, how do we calculate them? And well, this is for a simple type of structure, it's a very straightforward exercise. So if we go back to this rectangular mass attached to these 4 tethers, well, to calculate the mass, what we need to do is just find the volume and multiply by the density of the material. To calculate the stiffness of the springs, well, we can go and solve the differential equations of the bending of the beams, and we can come up with closed form expressions that for most beams look something like this. And so what this is telling us is that the stiffness is proportional to E, which is the Young's modulus, so higher Young's modulus, higher stiffness. It's inversely proportional to the length cubed, so if we want lower stiffness, obviously we make this longer. And it's proportional to this I, which is the second moment of area, that is a function of the cross-section of that beam. So for a rectangular type of structure, it's directly proportional to the width, or this value B, which is where the deflection, the orientation along which the deflection is taking place, and then proportional to the height. So we can very easily play with these parameters to change the overall mass or the overall stiffness that we want to get to achieve a particular scale factor, which is a function of your resonance frequency. And that constant value Cn is a function of your boundary conditions and the locations of your forces. So it's going to change depending on where the force or the boundary is located. So we can see we have different numbers for situations in which the forces, for example, a shear force applied to the beam, or a point load in the middle of the tether. So far we have discussed only the static response of accelerometers, but obviously these devices, like any other second-order system structure, has dynamics associated with it. And well, the response of this dynamic behavior is mostly attributed to the quality factor, to support gyroscopes, which is a function, it's inversely proportional to your damping B. So if we take a look at in the frequency domain, or the S domain, the transfer function from the mechanical part of the accelerometer using for acceleration to output displacement, you see that for very small input frequencies, so when the frequency of the acceleration you're applying is much smaller than the resonance frequency of the structure, this can be approximated to 1 over omega squared, which is the exact same expression that we got from that static analysis at the beginning of the presentation. Now, what this is telling us is that if my input is much lower than this resonance frequency, then my scale factor is going to be fairly constant in this range. So in most situations, this is true. Resonance frequencies of accelerometers are in the kilohertz to tens of kilohertz range, and usually you want to measure accelerations of no more of a kilohertz or so. So now the question is, well, why should I worry about the dynamics if my inputs are only going to be this range? Well, obviously in reality, our inputs are not going to be sinusoidal, right? We're going to have either impulse responses, like for example when we drop our part, or step type responses. And as we know, those type of inputs in the frequency domain are going to have high frequency content, and then we're going to get amplification around areas where we have high Q. So if we take, for example, a part with a Q of about 2, we see that we get this overshoot and reading response that is going to have some settling time. And so for accelerometers, having high Q is detrimental because your settling time is going to be much longer. So we will have to wait for the signal to settle down before we can take our next measurement. And also because we can get this overshoot that is going to surpass the displacement that we're trying to measure. And if the Q is too high, then this displacement can be so large that you can overpass your stability point of your cooling, and then the device can just touch the electrode and basically break. So obviously what we want is to have low Q, but not too low that it starts affecting our bandwidth. So ideally what you want is to have a Q of about 0.5 to 0.7. So now going back to what determines the quality factor in accelerometers, we can, similar to what we did for the gyroscope, we can break it down into different components, but since accelerometers are much lower frequency structures, the dominant source of loss is usually squeeze film damping. Squeeze film damping can be explained as the energy lost during the process of, for example, a parallel plate moving towards a fixed electrode. So when this happens, it creates a pressure distribution in this channel, and well, the motion of the plate has to put some energy to move out the molecules of the gas that are in between. And in this process, these molecules heat up, and as we know, heat is pretty much an irreversible process, so the energy that we put into this is lost. And this type of losses can be modeled by using the Reynolds equation, which is a particular case of the Navier-Stokes equation that describes the behavior of fluids. But for specific cases in which you have your fluid or your gas in between narrow channels, and as we can see from this expression, what this is relating is the pressure distribution in the channel to a rate of change of that gap. And as we know, damping is basically a force divided by a velocity, right? So if we solve this equation and we find the ratio of that pressure, which can be associated to a force by dividing by the overall plate area, and find the ratio with respect to that velocity, then that can give us an idea of this damping constant. So if we apply the right boundary conditions and make the right assumptions, which include assuming that the change in pressure is much smaller than the overall pressure in the system, that the change in the gap is much smaller than the overall gap, we can come up with closed form expressions for these simplified structures that might be a little bit idealistic for certain applications, but we can get a lot of information from them still. For example, we can see that the damping constants are inversely proportional to the gap Q. So this tells us that as we make our gaps smaller and smaller, we get much higher damping. So that way we can start thinking that, well, if we need to put a device in a low pressure environment, well, maybe if we make our gaps smaller, we can increase the damping, and then we can co-integrate this with gyroscopes. Something that we should watch out for, though, is the region of operation. So that is basically dependent on this parameter known as the Knudsen number. So what this is telling us is basically a ratio of the mean free path of the molecules to the size of the gap. So when the Knudsen number is small, which means that either your mean free path is small or your gap is big, we're in this regime called the viscous regime. So basically having a large gap tells us that there's not a lot of interaction between those molecules and the moving plate itself. Now, as this number becomes bigger and bigger by either decreasing our gap or by increasing our mean free path through a change in pressure, then we can no longer neglect the interaction of those molecules with the moving plate. So in those situations, this type of closed form expressions can no longer be used, but luckily there has been a lot of work around this type of operation in this rarefied gas regime, and there are numerical expressions that can actually help us account for some of the effects that you don't get in the viscous regime, like for example the fluid wall correction, which accounts for the absorption rate of these molecules to the plate, or for non-trivial boundary conditions, in which you no longer assume that the pressure at the edges of the plate is no longer zero, but there's a region of decay. And you can find in literature closed form expressions that take into consideration all this. Unfortunately, this is only for very simplified structures, so basically parallel plate type of devices. But if the motion is not exactly parallel, things start getting a little bit more complicated. Now, luckily, finite element analysis tools have advanced quite significantly in the past 5 years or so, and now most of them incorporate this squeeze film damping models that take into consideration all these non-ideal effects, and you can actually get very accurate closed form solutions or numerical solutions for your damping. This is an example of a simple beam run in ANSYS and in console, and you can get your pressure distribution and get an estimation of your damping. And they have actually incorporated really nice elements that can actually model, for example, reusals. So these will account for the fluid coming out of reusals that are in, for example, a carlos type of device, like the one shown here. So by the use of these tools, we can get a very good estimate of what our squeeze film damping Q value can be. So now the question, as I mentioned before, is how can we take advantage of this knowledge to actually incorporate accelerometers in a low pressure environment to coexist with gyroscopes? And well, we can do this, but obviously, as we've seen, as we decrease the pressure of our system, usually our Q goes up. But if we take a look at this simplified expression, there are many other parameters we can play with to compensate for the decrease in the effective viscosity, like I mentioned before. For example, the gap size or the electrode area. So if we make this very small and add several electrodes, then we can basically bring this damping number back up again, even in a low pressure environment. And an important thing to highlight is that before we do this, we need to see what are the effects of having narrow gaps in capacitive accelerometers. So if we look at the scale factor, for example, well, having narrow capacitive gaps is beneficial because your scale factor goes up. And this is actually really good because you can take off part of the load that you were putting into lowering your resonance frequency to get this high scale factor. And you can actually design much stiffer devices that can have much higher bandwidth and can be a lot more robust and gain back your scale factor by making this gap smaller. Now, one of the limitations of this is pulling voltage. So, as we know, when we apply voltages to a moving structure and a fixed plate, there's going to be an electrostatic force, and basically this is an unstable system that when you surpass this pulling potential, it's just going to cause the mass to just go and stick into your electrode. And as we see here, well, this is a very strong function of your gap, so smaller gaps means lower pulling voltage. So an alternative technique is to add additional electrodes, but then connect them at the same voltage as what your proof mass has. Since damping doesn't really care much about what the voltage is in those electrodes, we can just basically leave our sensing electrodes to be, the typical electrodes that we had, and then add a series of additional electrodes that are at the same potential, and that way we get an effective additional damping coming from the number of electrodes plus the number of damping electrodes. And that way you can implement triaxial accelerometers. You can use this exact same concept and implement it in out-of-plane structures. Here what you can do is, let's say, additional plate areas that are connected also to the proof mass in terms of voltage, and have additional squeeze film damping. This shows the mode shape of this particular triaxial accelerometer, and this is an SEM view of the x-axis accelerometer in that device, and we can see this very narrow capacitive gap that we get from this particular process. And here we see our electrodes that are measure this in capacitance, and this one's are the electrodes that are in mass and that additional damping. Then you can interface these devices with electronics, and here we see a wafer-level package MEMS accelerometer that is at the same vacuum level as the gyroscopes that we described in the previous session. So this is in an environment of about 1 to 10 torque, and as we see, we get a very nice response to acceleration for the x and y axis devices. We get the scale factor that is fairly close to the one for the z axis, and you can design the structures to have similar sensitivities by adjusting the masses and the stiffness of the tethers that cause that deformation. Yeah.
You said the gyros, there's a gyro for
1 to 10 torque, yes. Right.
The gyros are the
well, that's for tuning for gyroscopes, right? If you want to get cues in the order of tens of thousands in a low frequency gyro, you need to be in the millivolts. Now, if we take a look at the cues for a volt acoustic mode gyro, which is at a much higher frequency and doesn't get affected significantly by squeeze film damping, then you can vacuum package those devices at 1 to 10 torque and still get cues in the order of 50 to 200,000. In the previous session, I showed a device that had a Q of 77,000 about 1 to 10 torque. So that way we can integrate them with accelerometers.
And do these devices Q is linear distortional pressure?
No. So that's why it's complicated, and finite element analysis tools are usually beneficial. When you're operating in this regime of low pressures, your expected viscosity and this is an empirical type of expression. It's given by this type of expression where this Ks is your nonsense number, and this nonsense number is a function of pressure. So basically, you can replace this Ks here, and then this lambda here, and then you get what the function of this effective viscosity is going to be with the function of pressure. So you can basically see that here. This is a log plot. And you see that the Q as a function of this number, which is for the inversely proportional to pressure, or inversely proportional to pressure, you see kind of linear behavior in a log scale.
Comparison.
Yeah.
So that raises the question how we want this Q to be not as well as 0.5 and not as much as 1. So we want the Q to be 0.7.
Yeah, so
seal this thing with 2.24 and have it stay that way forever.
Yeah, so what you usually do is you design for a much lower Q at the risk of having lower bandwidth. And if you don't meet your bandwidth specifications, what you can do is through electronics do a closed loop implementation to regain your bandwidth. So what we usually do is design for Qs in the order of 0.05 or so. Then you gain back with electronics what you lost through feedback.
Vibration rectification effect?
Vibration rectification? I'm not familiar.
Well, where it tends to suck down to one surface and one other. Essentially, if you suck down, you produce a different source than on the way out.
Oh, I don't think that's related to your damping factor. That is actually related to the forces between your surfaces, right? So that's going to be like van der Waals forces between the interaction of the two plates. Usually having smoother plates is worse because they tend to attract a lot better. If you have rough surfaces, your forces are much smaller because the contact areas are small due to this roughness, right? But I don't think the squeeze film damping really plays a major role on this.
What about the temperature? The molecule will get a lot more energetic.
Yeah, so obviously with temperature, as I think Mostawa highlighted in the first session, your Q changes. So you can compensate for that two ways. You can either do a closed loop implementation in which, as I said, your bandwidth is no longer depending on your Q. Or you can do an open loop type of compensation. So you basically characterize your device, see how much your Q is changing, and then do a linear correction or a quadratic correction. Yep.
You showed us next some product plates for dancing and other product plates for dancing.
Mm-hmm.
Is there like an option? I mean, if you use also the product plate that you have for dancing, but we lower the voltage for the readout, isn't that more confusing?
Yeah, definitely. So actually, when you interface accelerometers with electronics, what you always try to do is to make that potential difference always zero. And I'll talk a little bit about the interface circuitry and how you accomplish this. The problem with that is that you still need to deal with processing. So you can't really make these gaps extremely small because obviously during the release of the structures there's always stiction. So there's also a limitation. And I use the pulling voltage as a metric because your stiction is usually associated to how much voltage you can afford having across the structure. So that's the major problem. That's why you have to be careful. And as I mentioned before, the way you can get around that is by actually designing a stiffer structure, right? Since you're making your gap smaller, you can compensate for the loss in scale factor. You're compensating for the loss in the scale factor that you lose when you make your frequency higher. So that's a way to get around that. For example, this device have resonance frequencies in the around 20 to 25 kilohertz. If you compare it with most commercial structures, yeah, it's quite high. So if you compare it, like for example, in MEMS RST accelerometers, they're in the order of a few kilohertz, so 2 kilohertz. So this is about an order of magnitude higher. But since you have such small gaps, then you get the same type of scale factors. So we can apply this same concept to single proof mass triaxial accelerometers. So obviously, in the consumer space, in sizes of so much importance, having 3 separate proof masses for X, Y, and Z obviously doesn't give you the best advantage in terms of area. So you can come up with structures that actually respond to acceleration about the 3 axes, the X, Y, and Z. In this particular case, we have this pendulum-like type of structure in which when you applied acceleration along the x-axis, it has this type of torsional motion, and then if you read out your signal by combining capacitor C1 and C2 and capacitor C3 and C4, you can measure a differential change in capacitance for x-axis acceleration. Similarly, if you now apply a y-axis acceleration, all you have to do is change the combination of capacitors. So basically now you combine C1 and C4 and C2 and C3, you measure the differential change, and then you can extract the y-axis signal. And as you can see, these two modes, and when you combine the electrodes are orthogonal to each other, so you reject any x-axis component from this measurement. And in a similar way, you can detect z-axis acceleration by now adding up all the capacitance of the 4 electrodes and comparing it to other capacitance. You could also measure differential z-axis acceleration by using that technique that I showed before, where you place electrodes attached to the proof mass, and then you get differential changes for the same deflection. And then you can take these structures. Yep. Excuse me.
The sensor, the mass sensor,
yeah. No, so the reason it was at this torsional moment is because when you apply z-axis acceleration on this spring, then it's actually going to stop it to then, right? And then the capacitors are only those stop electrodes are only to measure the change in capacitance. You're not actually applying an electrostatic signal to move it. What you want is actually to avoid that. You don't want any electrostatic forces. You want your change in capacitance to be purely because of your acceleration. Yep. Excuse me? Yeah, so actually the springs, I don't know if you can see it here, are on a separate layer of the proof mass. So in this particular case, this was implemented in an SOI wafer, and the proof mass is part of that device layer, so it's about 40 microns, and then you can bucket oxide and pattern it, and then the bucket is polysilicon, and then you can etch polysilicon. That's what defines that top cross-shaped beam and the electrodes. So you need those additional extra processing steps in order to generate these structures. So then you can take this type of devices, this single proof mass triaxial accelerometers, and co-integrate them with gyroscopes, and as we can see here in this plot, the devices were characterized before doing the wafer-level packaging in a vacuum chamber, and as you can see, for pressure levels of 200 millitorr and above, you don't get this Q-seeking response in the accelerometer anymore. So back to your point, since you're not seeing Q being at 200 millitorr, obviously at 1 to 10 torr, you're going to get about 0.05 of Q. So you're obviously compromising your bandwidth when you do this. So then you can interface this type of devices with electronics, and very similar to what we saw for this individual proof mass type of sensors, you can extract your sensitivity, and as you can see, one of the main concerns of this type of devices is cross-axis sensitivity, because any imperfection in the processing can make the proof mass to be slightly slant to a side, so you're going to get X or Y axis response when you're not supposed to. But if you have decent enough processing, you can see that you can get very decent scale cross-axis sensitivity. For this particular device, is about 1 to 3% of cross-axis. Now that's a high number for a consumer application, but you can always use, this is with no compensation, you can always use electronic compensation. If you do a characterization of how much cross-axis you're getting, you can null that out, assuming that you're not going to see any major changes across temperature. So far we have discussed techniques to implement these static type accelerometers in low pressure environments, but there might be situations in which this might not be possible. For example, if you're in your process flow, you don't have the ability to make these very narrow capacitive gaps, or if, for example, you want to co-integrate your accelerometers with tuning fork structures in which you can't really get decent Qs in 1 to 10 torr environments, but you need to go to the millitorr range. So once you go such low pressures, this technique of using smaller gaps might not be as effective. So you need to come up with a different way to co-integrate your accelerometers. And one way to do this is by not operating the device as a static sensor, but to use it as a resonator. So basically, if we take, for example, this beam, a MEMS beam type resonator, we know that that's going to have a resonance frequency for its fundamental mode that we have been mentioning. It's the square root of the stiffness over the mass. And if we find a way to make this value of frequency a function of acceleration, then by using a PLL or a frequency counter, we can measure this delta in frequency and extract a component of the acceleration. So one way to do this is by, for example, mass loading our resonator. So if we attach a proof mass to one of the ends of this resonating beam, and this proof mass is free to move, when we apply an acceleration, for example, about the z-axis, obviously this proof mass is going to try to move downwards due to Newton's second law of motion. And what that is going to generate is a torsion moment in this spring right here. And that torsion is going to create a tension, and that tension can be viewed as a change in the stiffness. So that way, what we have accomplished is to make that resonance frequency a function of our acceleration. And here's an example of this type of devices. Here we see that we have our proof mass that is anchored to some springs to to import resonators, and later on we'll discuss why is it important to have 2 resonators instead of just 1. Now, one of the limitations of this approach is that any process imperfections can actually make that movements to be slightly offset, and you can end up with drift in the resonance frequency. So another technique that we can utilize is not by loading the stiffness through a mechanical structure, but actually using the effect of electrostatic spring softening. So electrostatic spring softening is basically an effect that you see in micromechanical structures, in which if you have a parallel plate type of sensor or resonator, as we've been discussing, this has a nonlinear function for the changing capacitance for change of gap. So if we actually break down this nonlinear function as a Taylor expansion, we see that we have several harmonic components. One, the first one, which is our linear transfer function that we usually use for the derivation of our sensitivity, assuming that our reflection is not too large. But then we have a second term that is actually proportional to the displacement. And when we take a closer look to this, if we have a force that is multiplied by a constant times our displacement, well, that can be viewed as a stiffness. So basically, what this electric potential is causing is an effective or a virtual change in the overall stiffness of the structure. So now if we take our conventional accelerometer and we actually put it in a low vacuum environment, so it has a high Q, we can do the exact same thing that we discussed with gyroscopes. We can put it in a closed loop and make it resonate. And when we look at the equations of motion, now we have our second order mechanical transfer function. We have an input force due to the input acceleration, which is what we want to detect. And then we have this additional electrostatic force that is caused by the potential difference between our groove and the electrode. And as we showed in the previous slide, this has a component that is actually proportional to the displacement, and we can lump that together with the mechanical stiffness and call this whole term the effective stiffness of the device, and basically express our frequency as the square root of our mechanical stiffness minus the electrostatic stiffness, that, as we can see from the expression derived before, is a function of our gap. So basically, we have this device resonating, and once you have an acceleration, there's going to be a quasi-static changing gap that is going to change the electrostatic force between the electrode and the mass, and it's going to change the effective stiffness, and then we get an effective change in frequency due to acceleration. So one of the limitations of using resonant accelerometers is that most MEMS structures are made out of silicon or other type of materials that obviously have properties that are temperature dependent. So we can talk about mainly two terms. One is the dimensional change, which is a function of your coefficient of thermal expansion. So what this basically is how much are my dimensions changing, or my overall volume changing as I increase or decrease the temperature. And if we plug in this constant in the stiffness and mass terms of the resonance frequency, we can derive the dependency of that frequency of oscillation as a function of that alpha, which is a CP, or coefficient of thermal expansion. And obviously, what we see is that if we change temperature, our frequency is going to change. Very similarly, we can do the same for material properties like the Young's modulus. As we know, our stiffness is proportional to the Young's modulus, so our frequency is proportional to the square root of the Young's modulus, and then we get a frequency dependency on this material property. And for the particular case of silicon, the TCE is much larger than the CPE, so that's the dominant source of change in frequency. And if we compare this temperature dependency with a typical scale factor for a resonant accelerometer, what we see is that we're going to get about 20 to 60 milli-G per degree C of change. Now, to give you an idea of how bad of a problem this is, in commercial accelerometers for consumer applications, what you usually get is about 0.5 milli-G across your whole temperature range, which is about 120 degrees. So there are techniques that we can use in resonant accelerometers to get rid of this problem. And in general, what it's done is by the use of two resonators. So this is an example from ST Microelectronics, in which they have a large proof mat and 4 resonating beams, 2 of them for y-axis detection, 2 of them for x-axis detection. So basically, in the presence of acceleration, this mass is going to move, and as we saw before from that mass-loaded example, this beam is going to undergo a compression, this one is going to undergo tension. So we're going to get a differential change in frequency from these 2 resonators. And since the 2 of them are fabricated using the same material, then if we take the difference between these 2, the temperature dependency comes up as a common mode signal. So that way, by the use of more than one resonator, you can reject the temperature dependencies. Here's another example from UC Irvine, in which what they do is very similar to the ST Micro example. You have 2 resonators, but instead of using the tension and compression mechanical approach, they use the electrostatic spring softening approach that I described. So one of the resonators has a positive change in capacitance to a given acceleration, the other one has a negative change in capacitance. So you get a differential change in frequency, but then the temperature affects both of the resonators equally. So if you see the transfer function for input acceleration to change in frequency for 2 different temperatures, you see that they're right on top of each other. This is your rejecting that temperature dependency as a common mode signal. Yep.
But the proof of design is that spring softening type or mechanical?
No, it's the spring softening type. So basically what you have is a proof mat that is resonating back and forth, and you have this capacitor. So in the presence of an acceleration, let's say along the x-axis, for this resonator, this gap decreases, so your spring electrostatic spring constant goes down. In this case, if you see the location of the capacitor is on the other side of the mat, so the gap is going to increase, so then your effective frequency goes the other way. So it's a differential change. Yep.
Are any of these resonant accelerometers
No.
All the existing current productions?
Yeah. Well, I have never been able to find out how inventing accelerometers operate. I know that they are co-integrated with their gyroscopes, and I know that they consume a lot more power than conventional accelerometers. And obviously, in resonant accelerometers, since you need to close this loop and establish oscillation, you're definitely going to consume more power. So it makes me wonder if maybe they're using a closed loop resonant approach, but I'm
I'm not 100% sure.
One more question. As you described the electrostatic spring softening, it seems that I could almost use the same structure in a resonant setup as in a DC set.
In a resonant, I didn't understand.
Can I operate a DC accelerometer as a resonant accelerometer just by closing the loop on it, or do you design it as?
You can, but you need two loops now, right? You need
That's just electronics.
Yeah.
The same methods in either mode.
Yeah, actually, I think Arash is going to be discussing a little bit about the electronics of gyroscopes. And you can, a gyroscope is a resonant type of device, and you can close the loop around that one the same way that you do it for a static accelerometer. Yeah, that's the that approach. So you can linearize your output. All right, so now let's discuss a little bit about interfacing accelerometers with the front-end electronics. In general terms, probably the easiest way to measure a change in capacitance in a static accelerometer is by basically configuring it as some sort of capacitive bridge, in which what you do is you apply an AC voltage to the proof mass, and then by connecting the other end of the differential change in capacitance, so the two electrodes, to a TIA, you can establish a virtual ground here. So basically this potential is tied to ground, and then measure the current throughout that capacitor that is going to be equal to that input voltage times your impedance. And as you know, the impedance is for a capacitor is J omega times the total capacitance. And since this capacitor is changing with acceleration, when we measure the overall differential output, what we get is a changing voltage in the output of the TIA that is proportional to the feedback resistor. The resonance frequency, not the resonance frequency, the frequency of this excitation force times the amplitude of this excitation force. Now, the question is, well, once I apply an AC source to one end of my capacitor, well, that's going to generate an electrostatic force. How can I make sure that that force is not going to corrupt my acceleration measurement? Because all I want is a change in capacitance due to this change in acceleration. Well, a way to do that is just by basically taking the frequency of this source to be much higher than the 3 dB bandwidth of your mechanical structure. So basically, if this is changing fast enough, the MEMS accelerometer can really respond to that electrostatic force, and then you won't corrupt your measurement. Now, the problem of using this type of approach is that, well, first, you need to get a stable scale factor. You need to generate a very stable frequency and a very stable AC voltage. And this can be either complicated or it can consume a lot of power. Another problem is that trying to drive the node of the proof mass might also consume a lot of power, because usually the proof mass is connected to the rest of the substrate, so there's a lot of capacitance between that node and your ground. So you need to use a frequency source that is much higher than a few kilohertz, and then try to drive this huge load that obviously translates into higher power consumption. So, yep. Transimpedance amplifier. Yeah, so basically it amplifies a current into a voltage. So another method to interface accelerometers is by the use of this switch capacitor interface. This These type of circuits are advantageous because they're usually small in size, because all you need are switches and capacitors, which in ASICs they don't consume a lot of area. They're low power because, as we will see, you don't need to drive that huge node of the proof mass. They are flexible enough to implement noise reduction techniques like auto steering or correlated double sampling or chopping, which basically takes the noise of your amplifier and either samples it out or up converts it in frequency, so you can reject all that additional noise of your electronics. And they also allow for multiplexing, so this can help to use the same front-end electronics to sense different axes of interest, and they also facilitate the digitalization of the signal, because since it's a sample system, you have already done half of the process needed to digitize the signal. So the way these interfaces work is fairly simple. What you do is first you sample your capacitor. I don't know what happened there. I think this is not compatible with running it in a different laptop. But anyway, what this is the CP1, this is CP2, so basically the positive capacitor and this is the negative capacitor. Fairly easy to follow. So what you do is you basically connect in the first stage your MEMS capacitors to constant voltage, and what that does is it accumulates a charge that is going to be proportional to that capacitance. So obviously the capacitors that are changing in a positive direction are going to have much higher capacitance, so they're going to store more charge than the ones that are on the other side. And then during that time, you can sample the noise of your amplifier for correction in the next stage. And then what you do is then you connect those capacitors that have that stored charge, and basically the difference between the charge of the positive and the negative electrode goes into the amplifier and gets converted into a voltage that is proportional to our supply divided by the feedback capacitor of the amplifier. So unlike the other sensing techniques, you don't need a stable AC amplitude and a stable AC frequency. All you need is a stable DC source, which you can easily achieve by the use of regulators, and then the capacitor of the feedback that you can through digital selection change in order to get a particular scale factor. As I mentioned, another advantage of using switch capacitor interfaces is that you can measure multiple axes using the same electronics. So, for example, we have a biaxial accelerometer in which when you're detecting x-axis acceleration has a positive change in capacitor C2 and C3, but a negative change in C1 and C2 and C4, and then C1 and C3 is negative. But when you're detecting y-axis, the capacitors that are changed positively and negatively are different. What you can do is take your front-end switch cap amplifier and basically put a multiplexer in front of it. So you can allocate time slots to measure each axis. So for example, when this signal that corresponds to a measurement of the x-axis is high, what you do is this multiplexer is going to connect capacitors C1 and C3 to the positive input of the amplifier and C2 and C4 to the negative. And then in the next time slot assigned for the y-axis sensing, you just, with the multiplexer, change now the positive input to C1 and C2, and then semi-negative to T3 and T4. And that way you need 3 separate input or front-end stages for each of the axes you're trying to measure. Yep.
In the AC excitation approach, are we measuring all tensor lines simultaneously, where in this case is next one?
In the other approach, you will have to have 3 separate sources.
So we're measuring all of the time.
Yeah, constantly. In this one, you're allocating time slots between them. So what you usually do is you make the frequency of selection much higher than the minimum, or rather the maximum acceleration signal you want to measure, the maximum frequency of acceleration. So if, for example, your MEMS accelerometer has a bandwidth of 1 kilohertz, then you make this, you can make it 2 kilohertz, I guess, if you follow Nyquist's principle. But ideally, you want to oversample it, so you make it 10 times or 20 times larger. So that way you don't lose a lot of information during the sampling.
Is there any circumstance in which the AC measurement technique is perfect? It seems like this would almost always be better.
That's a very good question. I really don't know, but I know that it's used a lot. I know that Honeywell uses it. I don't see why it would be more advantageous, really.
I don't know about commercial products. I think you need to characterize your device for that.
Yeah, I mean, if you're using discrete electronics, the first technique is a lot easier to implement, but if you have an ASIC, I don't see why you wouldn't go with this approach. I really. The other one is probably, if you're not a circuit designer, it's just probably easier.
Yeah.
All right, so now let's talk a little bit about this problem that we have been discussing with the nonlinearity of parallel plate transducers. So as we said, for a parallel plate, our changing capacitance due to a changing gap is a nonlinear function. So we're limited to the amount of displacement that we can measure before we start compromising the linearity of our device. So one way to get around this is by using a feedback approach, in which you have your conventional accelerometer and your parallel plate capacitors CS and CR. But in addition to this, you have another set of electrodes that you can use to apply an electrostatic force of equal value to the force due to the acceleration. So basically, if those two forces are equal, then the movement itself is not moving. So if you don't have any change in capacitance, then if you don't have any change in gap, then you don't have this nonlinearity problem. And the way you can do this is by applying feedback. So basically, you measure your signal from your conventional electrodes, and then you sample it and feed it back into this electrostatic force generation type of electrodes, and then your overall output signal is now not a measure of your changing gap, but a measure of the amount of energy, the amount of force that you need to apply to keep the device fixed in space. The advantage of doing this is that it linearizes our output, as I mentioned, because the mass is not moving. Similar to what happens in an amplifier when you apply feedback, your bandwidth is going to increase. But injecting that additional force degrades your noise, because you're now putting an additional amplifier to drive this device, and obviously it increases complexity because now you have to worry about stability, and it can increase power consumption depending on the parasitic capacitances that you need to be driving. So now let's talk a little bit about one of the major challenges in commercializing accelerometers, and that is calibration and compensation. So one of the reasons this is of great importance is because usually when you're trying to put out a product, most of the expenses come actually from your testing. So if we take, for example, a typical MEMS device, usually what you do is you get your wafers and you do an initial probing to see which devices survived the process and which ones didn't, and you dice your wafer and the parts that you found from this probing, you package them. But in inertial sensors, we need to go through a calibration process in order to compensate for any process variations. And the typical way of doing this is by placing part by part on an equipment that can produce a physical stimulus. So, for example, in an accelerometer, we will have to put this on a shaker table, measure the scale factor, compare it with a reference, and then if for some reason in the processing that scale factor doesn't really meet what your product has to deliver, then we have to go and change, for example, the gain settings of our electronics to make sure that the value is right where we want it to be. And obviously, if you need to do this for every single part, this is going to be very time-consuming and very expensive. In MEMS in particular, this is the case because we usually have to use unconventional testing methods, like, for example, vacuum probers and shaker tables and rate tables. So all this different physical stimulus type of testing can be very time-consuming. So a way to get around this problem, particularly for accelerometers, is by using a no physical stimulus type of calibration. So as we've been discussing, in a conventional accelerometer, when you have acceleration, you have a change in the displacement, and you measure your change in capacitance. Now, we could take this same structure and now turn it into an actuator. So if we take a separate electrode and we apply a voltage, then we can cause a displacement and get a transfer function for the change in capacitance for change in voltage, and then relate these two expressions, and we can basically emulate that acceleration by the use of a voltage, and that way we don't need to be placing part by part in a shaker table and do the calibration in a much faster and efficient way. Obviously, in the lab, this is very beneficial, but the real advantage of this type of approach is that you can actually implement this calibration method in the circuit itself. And this can be of great importance in applications where you need, for example, to store a device with an accelerometer for a long period of time. And if, for example, this is in a medium or high vacuum environment, as time progresses, the performance of the sensor is going to change. So when it comes time to use the instrument that has the accelerometer, you don't want to have to replace that part or have to take the part back to the lab and recalibrate it. What you want is to be able to turn it on for the part to recalibrate itself and then be able to operate. So this non-physical stimulus calibration can be implemented in the form of a built-in test, and then you can basically recalibrate your parts. Yep.
Is that including parts in it?
Yeah. I don't think every time you turn them on, but they definitely have a built-in test mode. I know that for analog devices parts, you have this feedback control that actually creates this electrostatic force. But I don't think it goes through it every single time. I think it's a one-time calibration once you place the part and wherever it has to go. I don't know if maybe you have the possibility of going back and reprogramming to do it every single time.
How can you rely on the performance of the recalibration? If it's related from the electrostatic force, so it can also have some lifetime or dependency.
Yeah, obviously there are limitations associated with this type of calibration. If, for example, the gap between the electrode that you're using to produce that force changes differently than the gap that you use to sense your acceleration, for example, then you're going to have an error associated with that. But obviously, these errors are going to be generally much smaller than what you're trying to calibrate for. So there are definitely limitations to the technique. So far we have discussed methods to calibrate scale factor, but another very important parameter in accelerometers is offset. So as we described earlier on, offset is basically a signal at the output, even in the absence of any applied acceleration. And there are many sources by which we can get offset. Obviously, the typical one is when your initial capacitors are not exactly identical. So obviously, your output voltage is a function of the changing capacitance due to acceleration, which is a signal that we actually want to use, and this defines our sensitivity. But if these capacitors are not equal to start with, then we're also going to get an output voltage that is going to be proportional to that difference. So obviously, we need to find ways to calibrate this out. A simple way to do this is by placing a capacitor bank at the input of our front-end electronics. So if before we operate the accelerometer, we just measure the offset at the output, and then start changing the switches that connect either the capacitors in series or in parallel. We can, by trying to match the differences in capacitance, we can bring that offset level down to 0. Now, the problem with this technique is that it's obviously limited by the minimum capacitor that you can get from your electronics. And it's gonna, if you start trying to make this capacitor smaller and smaller, then the parasitics of the ASIC are going to start dominating, and it starts becoming a nonlinear function. So an alternative method is by combining this capacitor bank. Oh, and we got again this weird symbol here. But in general terms, so what you want is to use that capacitor bank. But in addition to this, what you do is you add a calibration voltage. So as we described before, since what really matters is to measure the difference in charge between our positive and negative capacitors, we can allocate a time slot during the switching process of the reading of the capacitors to apply a voltage that balances out the charge of the positive and the negative chain of the differential sensing. And the reason this is advantageous is because usually getting finer steps in voltage is a lot easier than getting fine steps in capacitance. And here's an example of a calibration done on an accelerometer by changing the calibration voltage. And as you can see, we can get this close to the common mode value, which is basically half of your supply. And if you implement much finer steps, then you can get much better resolution and cancel out your offset. And then if you need to take care of this across temperature, well, you can put slopes on this voltage, unlike what you do with the capacitors, because they're digitally selected. Those slopes can be temperature dependent and then correct for this offset across temperature. So most of today's discussion, or probably all of today's discussion, was around this structural MEMS sensors, but it's always good to take a look at what other type of devices are out there. And in the first session of today's talk, Moshava described this thermal type of accelerometer in which you don't have any moving parts, so you don't have this solid proof mass attached with tethers to anchors. But what you do is you basically create a cavity and you fill it with a particular gas, and then you, by the use of a heater, you basically heat up a certain region of that cavity. And then in the presence of acceleration, the inertia of that heated portion is different than the rest of the gas in the cavity. So basically, you can measure differences in temperature between the thermocouples that are right next to the heated region. Now, the reason this is of great interest is because if you don't have any moving structures, it's highly reliable and very low cost. Your yields are usually pretty high. The problem is that since you don't have that large mass, that, as we described, is very important to reduce the resonance frequency, then your noise performance is not as great. Another type of accelerometers are this tunneling sensing type of structures, in which by using micromachining, we define these very sharp needles that when they change, when the gap between that needle and a parallel plate changes, then your tunneling current changes dramatically, so you can get very high sensitivity with this approach. The problem is that that current is very dependent on the ability of that, and it also changes very erratically across temperature. So I just put these two examples as some alternative techniques that are still under research. And with that, I pretty much conclude today's talks. This is a summary of what we went over today. So thank you very much.